Deep inside the forgotten archives of Cold War aerospace design, conventional physics encountered an impossible anomaly. For nearly a century, every aircraft ever engineered was bound to a catastrophic aerodynamic limitation. If a wing moves too slowly, the airflow separates, lift completely vanishes, and a multi-million-dollar machine falls directly out of the sky. This single point of failure has claimed thousands of lives and cost trillions in lost hardware. But in 1953, a radically engineered machine rolled out of a silo, defied basic fluid dynamics, and would stall before ever leaving the runway. They were entirely wrong. The moment the throttles were advanced, the propellers didn't just pull the aircraft forward. They forced high-velocity air directly through the curved channels, compressing the airflow and generating massive lift while the fuselage was barely moving. It didn't look like flight. It looked like an unnatural physical manipulation. Witnesses described the prototype lifting off the ground at an astonishing 22 miles per hour, taking off in less than 100 feet, and executing extreme banking maneuvers at speeds that would instantly send a conventional fighter into a fatal spin. The aircraft was virtually unstallable. To truly understand why this asset was buried, one must look at the brutal mathematical reality confronting defense planners in the mid-20th century. Air superiority was shifting toward raw, unadulterated speed. The Pentagon was heavily funding multi-million-dollar supersonic interceptors, sleek titanium hulls built to outrun Soviet radar networks. These projects required miles of pristine, reinforced concrete runways to build up the immense speed necessary to achieve lift. The U-Wing project, officially designated under the Custer Channel Wing architecture, stood in direct defiance of this entire doctrine. It proposed a radical counter-logic. True aerial supremacy wasn't about flying faster than the speed of sound. It was about the absolute control of ultra-low velocities. If an operational military transport could take off from a mud track, a dense jungle clearing, or the damaged deck of an aircraft carrier without catapult assistance, the entire logistical framework of global warfare would change overnight. The U.S. military immediately took notice, realizing the catastrophic strategic advantage of a fixed-wing asset that could operate completely independent of vulnerable base infrastructures. Navy evaluation teams closely monitored the test fights, stunned by the realization that this bizarre machine could effectively hover in a strong headwind while maintaining perfect control surface responsiveness. It was a capability previously restricted to early, mechanically fragile helicopters, but the U-Wing achieved it with the structural integrity and payload capacity of a fixed-wing transport. Yet, despite its flawless aerodynamic performance, the project quietly vanished into obscurity, buried by a combination of corporate defense lobbying, institutional skepticism, and primitive mid-century manufacturing materials that couldn't safely mass-produce the complex channel wing design. For 70 years, the U-Wing was catalogued as a historical footnote, an eccentric design left to gather dust in isolated aviation museums. But quietly, inside elite modern defense laboratories, the calculus has changed. The structural limitations of 1953 no longer exist. The rise of lightweight carbon fiber composites, ultra-dense electric propulsion systems, and automated digital flight controls has suddenly unlocked the true potential of the channel wing. Modern defense contractors are now resurrecting this suppressed 1950s blueprint to develop autonomous heavy payload cargo drones and silent stealth transport platforms that can hover without complex tilt-rotor mechanics. The impossible design everyone laughed at wasn't a failure. It was a highly advanced asset, waiting for the rest of human technology to catch up to its calculus. For 70 years, the U-Wing was systematically catalogued as a historical footnote, an eccentric design left to gather dust in isolated aviation museums, while the military-industrial complex poured trillions into conventional runways and high-maintenance tilt-rotor platforms. But quietly, inside elite modern defense laboratories, the geopolitical calculus has fundamentally changed. The structural and material limitations of 1953 no longer exist. The primary vulnerability that terrified mid-century Navy evaluation teams was the lethal engineering paradox of asymmetric thrust. In a dual-engine piston setup, if a single engine suffered a mechanical failure during a critical low-speed hover, the immediate and total loss of airflow through that single channel would cause one wing to stall instantly, while the other continued generating massive lift. The result was a violent, unrecoverable roll that would plunge the asset directly into the dirt before the pilot could calculate a countermeasure. Mid-century analog flight controls simply weren't fast enough to counter fluid dynamic failures of this magnitude. But today, the dawn of distributed electric propulsion, DEP, has entirely rewritten the laws of aerodynamic survivability. Instead of relying on two volatile, massive combustion engines, modern aerospace engineers are skinning the inner arc of the channel wing with arrays of synchronized, high-output electric microturbines governed by autonomous, thousands of hertz digital flight control computers. If one microturbine fails, the automated system adjusts the voltage across the remaining units in microseconds, maintaining a flawless, mathematically perfect lift profile across the boundary layer control matrix. Furthermore, this modern configuration unlocks an untrackable tactical asset, vectorized aeroacoustic masking. By burying a dense network of electric fans deep within the acoustic shadow of the semicircular channel, the wing structure itself acts as a massive physical sound barrier, absorbing the high-frequency engine whine and directing it purely upward into the sky. To an adversary standing on the ground, a heavy payload cargo drone utilizing this architecture wouldn't just be invisible to radar due to its blended carbon fiber geometry, it would be completely silent until it was directly overhead. Modern defense contractors are now actively resurrecting this suppressed 1950s blueprint to bypass the exact geopolitical logistical friction that breaks modern supply chains. In a near-peer conflict, massive concrete airfields are the very first assets neutralized by long-range ballistic missile strikes. When the runways are cratered and burning, the military that commands the skies will be the one that doesn't need a runway to fight. The impossible channel wing design that conventional aviation experts laughed at wasn't a historical failure. It was a highly classified, hyper-advanced aerodynamic asset waiting for modern computing and lightweight carbon composites to finally catch up to its calculus.